Okay, so now we are going to define, well, first of all, let's take a look what we have done. We have the vector of derivatives on the left-hand side in here, and we have the A matrix over here. This is the state variable vector in this case. Y1 is a position, Y2 is a velocity, Y3 is a position again, and Y4 is a velocity. And this, we have those two sources, and I just made a small correction because I miswrote here. This is the B matrix, and this would be the U vector. That's the way we have it. So our objective, I would say, why don't we put it in here, maybe some notes in here. We did the transformation in here. And then let's go here. Step number 5 was write the equations in first order form into the state space form. In here we obtain, say right there, say we obtain the A and B matrices. Step number 6 would be define the output equations. And the last step would be write the equations, and we say the output equations to find the C and the D matrices. And that's what we want to do right now. So let's just set as an objective that our output is going to be the force on this spring and the force on this damper. So why don't I'll just write it down in here. Say let's define what they are. Just put the title in here and say outputs. We define what the outputs are. We're going to say is the force on the damper, and also the other output is going to be force on bottom spring. So we write let's call this force D, and this call it force Fs for a spring. So let's just go over here. What is that force? That means the force is this one, right, on the damper, right here, isn't it true? So let's just write down the force on the damper in here is going to be force on the damper. But let's just change colors to make it a little more interesting. So it's force on the damper is going to be minus k sub 1, minus b sub 1 times x sub 1 dot minus x2 dot. Yeah, that's my first output equation. And the force on the spring is going to be minus k sub 2 times x sub 2. So in here, remember, this would be minus b1 times what's x1 dot? Go to the coordinate transformation over here. X1 dot is Y2, right? See? So this X1 dot is Y2. And what is this X sub 2 dot? If you go to the coordinate transformation, X sub 2 dot, right here, is Y sub 4, because it's dy3 dt is X sub 2 dot. So that is going to be minus Y sub 4. And then my other output equation is going to be minus K sub 2 multiplied by, what's X sub 2? Go to the coordinate transformation. X sub 2 is this one, right there. It's Y sub 3. It doesn't seem like it, but we have the total information that we need to write the output equations. So what I'm going to do, consistent with the colors that I was using, I will put it in red here. We need to establish these matrices in here. This is going to be the same state vector. And then you will have the other matrix here. And then also the same state vector. What that means is this is going to be Y1, Y sub 2, Y sub 3, and Y sub 4. And this is going to be M1G and M2G. This is going to be force of the damper, and this is going to be force of the spring. So force of the damper right here, minus B sub 1. So for Y1 we have a 0. Let's just be consistent here. And then for Y2 we have a minus B sub 1. And then you have, don't worry, Y sub 3, so this is 0. And Y4 is a minus 1. And this, also these two are going to be zeros, because it has nothing of those terms on this output. Now this one right here, Y sub 3 is the one that we need. So Y1 is a 0, this is 0, this is minus K sub 2, and then this is 0, 2. And this also, these two are 0, 2, because it doesn't have any of those outputs in there. What we have done right now is we have created this form that you say is y is equal to C times the vector X like this, plus the matrix D times the vector U like this. So this is the second part of the state space form, because you know, this is the general, this is the form, you know, this is the form. We have obtained the C matrix is going to be this one right here, and the D matrix is going to be this. And with this we have completed completely the state space form for this example. You have the derivatives in here, right there, is equal to the matrix A times the state vector, and then the matrix B times this, and then we have the other matrix, the outputs in here in this form, C times the states plus D times the inputs. And this is the state space form. Yes?
In your first equation, the fourth variable,
this one.
you have a negative 1.
Yeah, because here.
A positive B1.
Oh yes, because of the multiplication here. Thank you. I think this is going to be plus 1.
A positive B1?
And it would be a B1, yes. Yeah, thank you. It's got to be like that. Well, there's several brains think better than one. So yes, that's the way it'll be. So with this, you have obtained a system that in general, in the general form of the state space form, in fact, if you look even in Simulink, you will have a block like this. We are doing things much professionally now, so I am going to get one of these, and then do it like this. In Simulink, you will have a block actually that looks like this. You will have the inputs in here like this, and it will say, and here we'll have like x dot is equal to a times x plus b times the vector u, like that. And it looks like this in the Simulink. This is the matrix C times x like this plus the matrix D times the vector u. And then you will have this. Of course, you could see that in here, this is the vector u, and this is the vector of this, the outputs, whatever you are going to have. You're going to have the, as outputs, you will have the y vector, right? This vector like this. And that way you could begin to see where we're going. You have the whole entire system into one of these blocks, and then build your control system around that.